Hi, good evening. In this particular video, we would be looking towards the concept which is called acceleration due to gravity. And we all know what is the value of that, that is 9.8 meter per second squared. If I take the rigid definition of what is acceleration due to gravity, we can call it as a body in free fall under the influence of Earth's gravity expressed as a rate of increase in velocity per unit time. This is per unit time. So I repeat, it is the body in free fall. Please note that there is a word called free fall under the influence of Earth's gravity expressed as a rate of increase in velocity per unit of time. Just to make things easier, acceleration produced in a body because of the Earth's gravitational force is called acceleration due to gravity. So acceleration produced in a body because of Earth's gravity is called acceleration due to gravity. Now, we will take a step-by-step approach in order to understand this concept. So first what we will do is that we are going to get over a very basic formula of Newtonian mechanics in order to find out how we can reduce this value. So taken what we have learned in our previous videos, we can call the force of gravity. I put it as a subscript G equals to M. I can just put it as 2 because I want to mention the a person standing on the surface of the earth equals to G, M2G. So just to quickly draw around to give an idea, just a basic idea. This is the earth and here is a person, or maybe it is me who is standing on the surface of the earth, and this is basically the radius, which we know it's 6371 kilometers. Just in the previous video we have seen that. So now this is force, that is a gravitational force equal to M2. This is the person times the G, that is the gravitational acceleration. We also know from the Newtonian mechanics, which we can put it forward, is that Fg equals to G, capital G, M1, M2 divided by R squared. We have find this numerous times. Now, because we can represent G as M2G, so in further, if I take forward, I can write it as M2G equals to capital G, M1, M2 divided by R squared, right? Now you see I have done a little bit of trick. I have deliberately written M2 as this is M2, this is me standing here. So I have deliberately written so that I can show you right here that this M2 and this M2 gets cancelled out. This M2 and M2 gets cancelled out, and what we are left is G equals to capital G M1 whole divided by R squared. Simple algebraic calculation, so we have arrived. Now this M1, which we called, we can rewrite this as 5.97 into 10 to the power 24, that is the mass of Earth. So I can just write over here in small, which we already know. So I'm just writing it over 5.972 multiplied by 10 to the power 24. Right, so this is the value. So I can, from here, what I can do is that I can quickly write the equation as G, that is what we are trying to find out, the gravitational acceleration of Earth. We already know this value, so I write it 6.67 minus 10 to the power minus 11 Newton meter squared kilogram squared. Now note that again I would be omitting right now the values, but it is important, as I always tell, that units are extremely important in this case. So what I will do is that I will write here 5.972. I am not showing the further calculations because you already know that is 10 to the power 24 kilograms, that is, this is the mass of Earth, and I whole divided by the radius squared. This is the radius. This is the radius. So this is R. And we already know the value of R. So what I will do over here is that I will just transfer this from kilometer to meter. So it is 6371 kilometers. So I do it as 6.371 multiplied by 10 to the power 6, because from million, 1000, 5 plus 1, 6 meters squared. Now you see, I have nothing more to show you. This is something from which you can quickly calculate the value of G, isn't it? But what again is very, very important is the conversion in terms of the value, that is the meters and kilometers and Newton meters. So what we have got right on the top, what we have got right on the top, we have got Newton meters squared. So just let me write it for the, it would be easier for you. So I write on the top Newton meters squared. So Newton meters squared by kilogram squared, this is the value. And here what we have got is the mass of Earth. So this is in terms of kilogram, right? And below what we have got another kilogram squared, Newton meter squared, kilogram squared, this one. And further I write it as meter squared. So this is Newton meter squared, kilogram squared multiplied kilogram whole divided by meter. This is one, this is one. So what we find, meter squared get cancelled out, kilogram squared and kilogram squared get cancelled out, and what we get is kilogram. Now let me write it for you in a different color, which would be easier for you to understand. From here what we are getting is that Newton kilogram, right? So these have got cancelled out, so we have got Newton kilogram. And what is 1 Newton? 1 Newton equals to 1 kilogram, so I can write it kg meter squared, right? So I just substitute this value over here, so it would become kilogram meter squared whole divided by kilogram, right? So we have got the value of Newton as 1 Newton equal to kilogram meter squared, and what we have got below, we have got Newton kg, so we put it, the kg comes below the Newton, so this one and this one gets cancelled out, and you see what we have got is meter per second squared. And that is exactly what we showed you right at the beginning. It is 9.8 meter per second squared. Now we can solve this further. I am not taking much time because you can solve it out later, and it will eventually lead to 9.8 meter per second squared. So this is the way in which we can find out the value of G. So this is one part of the video where we have shown you how you can calculate the value of G. Now, for example, I am taking another I'm taking another illustration which will make life easier for you. When we try to tell you what is meant by 9.8 meter per second squared, I can just show you a small demonstration over here, which probably we will be able to understand. So if a person, this is a height which I'm trying to show, and here we have got another person who is standing right at the top. I'm just going on for further illustrations, right, in order to make things understand. And he is dropping a ball, right? And this ball will be moving down in this path, right? So I can count it as 1 second, 2 seconds, 3 seconds, and 4 seconds, right? So I count this as 1, 2, and 3. And you note that this is 9.8 meter per second squared. So what I'm trying to tell you is that right at 0 or at the first second, it would be 9.8. Second, at the initial, it would be 9.8 plus 9.8. It would be 19.6. Further, it would go up and it would come down to 19.6 plus 9.8. Then it will come further to, it will come eventually to 34.2. I think 39.2, something like that. So you can just add up, it would lead to 8, this would come to 9.8, and this would be 19.6, 4, it would be 29.4. Now, in this way, and add another 19.6 over there, it would be 29.4 plus 19.6, it would come to, yeah, it would come to another value, which would be around 8, 29.4 plus 19.6, 49. So it would come to 49, and so on. So this increase in the value, what I'm trying to show you, this increase in the value, this is basically based on the 9.8 meters squared, how it is increasing first, second, third, fourth. So it will be increasing by 9.8 meters squared. Now from this, what I tried to show you exactly is that no matter what is the mass of two objects, it doesn't matter, but the gravitational acceleration falling would be always 9.8 meter per second square. See, if I've got a value in here as 1 kilogram, and I have got a bigger one, which is 10 kilograms, this is 1, this is 10. Now, if I try to demonstrate that the value of the falling of the mass of these two, this is mass M1, this is mass M2. So this would be falling, both of them would be falling at 9.8 meter per second square. 9.8 meter per second squared. So irrespective of the mass, just note my point, it doesn't matter what is the mass. Irrespective of the mass, the velocity will increase. The velocity is always going to increase, and it is going to accelerate at 9.8 meters per second squared, irrespective of the mass. So two bodies released from different heights reach the ground at different levels just because we have got an air friction. So this might reach a little bit earlier, this might a little bit later because of the air friction. But if it is done in perfect vacuum, if this experiment is performed at perfect vacuum, both of them are going to reach at velocity simultaneously, and they are going to fall at 9.8 meters per second square. And that is what exactly Galileo have done. And in the next part, what I'm going to demonstrate to you, just excuse me for turning my page, I'm going to show you how it has been achieved. Now, in the year 1589 to 1592, which we precisely don't know. So let us assume to be the year when at the University of Pisa, Galileo was a professor of astrophysics and mathematics. 1589 to 1592. That could be the approximate timeline. So what Galileo had done was that if this is considered to be the Leaning Tower of Pisa, he went right on the top and he dropped two balls. He dropped two balls, which is more or less of the same size. The density would be the same. The two balls of different masses. The two balls are of different masses, but with same shape and same density. When they actually reach the ground, they fall at the same rate. That is, that gravitational acceleration was around 9.8 meter per second square. So now you see from the earlier video or earlier illustration, what I tried to show you, that if this is a man who is standing right on the top and these two are falling down, then the first second would be 9.8 plus 9.8 plus 9.8 plus 9.8, and this is the way in which it is accelerated. Now, there was another person, we all have heard about him, the Greek philosopher, from which philosophy actually starts. Aristotle believed that the heavier objects fall faster. Now, in order to defy Aristotle, Galileo Galilei performed this experiment. But this is, I would say, in illustration, it is all okay. It's fine. But why don't we see it in terms of mathematical equations? So, just to make things easier, we know that force equals to ma, right? And we also know that force equals to g m1 m2 by r squared. This is m2 by r squared. Now, for example, if I draw Earth, for example, I'm drawing this on the Earth. This is right from the distance from the center, and this is a stone, which the Earth is pulling. So there's a gravitational acceleration. So what we can deduce from here, this is the stone, so I made S, and this is Earth. Now what we can find out right from here is that if we take this equation, force equals to ma, if we take this equation, force equals to ma, from here what we can find is acceleration equals to force by mass, right? Simple. So I put acceleration equals to force by mass. Now, for example, I am trying to get the acceleration of the stone. So what is the acceleration of the stone? It would be AS. I put the subscript as AS and I put it as F capital M. And what is the gravitational acceleration of the earth? I can put it as AE equals to F divided by, say for example, I put it as capital M because the mass of earth is far higher than that of the stone. Now what we can see over here is that this is the, so now what we can find is that what is the acceleration in terms of the stone. So what we see is that this is acceleration. This is acceleration. This is not of stone earth, but this is acceleration F by M. This is both. Now, if I want to calculate the acceleration of the stone, so acceleration is equals to force by mass. And what is force? This is force. So I am calculating the acceleration of stone. So I will take G M1 M2 divided by R squared whole divided by the mass of the stone, which I say, for example, if I take it as M1, say for example, or anything that I can take. So for example, I take it as M1. Let me take it as M2. Let me take it as M2. So this stone will be M2. This would be M1, just for convenience. Now you see what happens. This 2 cancels out and the acceleration stone will be something like G. I am taking, for example, M by R squared. So this is the gravitational acceleration of the stone. In similar way, what I can show you is that we can calculate the gravitational acceleration of earth. It would be similar, G M1 M2 whole divided by R squared by M1, that is the mass of the earth, which we mentioned as capital M. Anyway, it doesn't matter. M1 and M1 get cancelled out and it equals to G M2 by R squared. Now you might say that the gravitational acceleration of the stone will be less because of the mass being high. It is far off from the earth. But note one thing, that in both the cases, the gravitational acceleration of the earth and the gravitational acceleration of the stone, both the small m's are getting cancelled out. This one has cancelled out, this one has cancelled out. So whether be it a stone, whether be it is an earth, mass doesn't matter. So what I tried to show you previously, that if it is a 10 kilogram ball and a 1 kilogram ball in this particular page, which I would like to show you again. In this particular page, see, I told you that this 1 kilogram mass or 10 kilogram mass actually doesn't matter. The mass doesn't matter. The G will be the same. Here what we have deduced is exactly that one. So you see the acceleration of the stone, the m's, that is the mass of the stone, is getting cancelled out. Acceleration of earth, m, is getting cancelled out. That is the mass of the earth. So that is why it proves that Galileo is right. So that is how we can come to a conclusion what Galileo did at the Leaning Tower of Pisa. So mass is irrespective of the gravitational acceleration. Just one final point before we conclude to this video is that if you consider the earth, you know that earth cannot be considered as a perfect sphere or a circle. Technically we call it as an oblate spheroid. We call it oblate spheroid. So once we are, this runs the equator. That means it is a little bit fatter. It is a little bit longer in terms of the equator rather than on the pole. Now, if there is a person who is standing right at here, and if there is a person standing near the pole, there would be difference in terms of weight. Because weight here will be less. Because you are far from the center. If this is R, you are far from the center. And the gravitational acceleration will be lower. If you are right at the pole, that means you are nearer to the center of the earth. That is this R. So I can just write it. This one, where weight is less. So I can tell that W will be less. Because you are far from the radius, far from the center of the earth. Whereas right at the pole, your weight will be more. Because you are nearer to the pole. So although if you travel from here directly over here, the difference will be very less, like it will be imperceptibly less. We won't be able to measure until we have got those instruments. So this is how the difference is. So what we have finally come to a conclusion is that earlier we have seen in the video that how we can deduce the value of 9.8 meter per second squared. This is how we have come to the conclusion that we have taken the values, we have cancelled out the values, and what we have got is only meters per second square. And from there we have come to conclusion that whatever be the mass, 1 or 10, it would be falling at 9.8 meters per second square. Also, what is important is that this particular person, when is dropping at a velocity, this ball, it would be 9.8 and it would be increasing 1 by 1 by 1. But don't mind my values, that might be this calculation is wrong. It would be 9.8, 19.6 plus 9.8 and so on. In the next part of the video, what we have seen is that around 1589 to 1592, when Galileo performed this kind of an experiment, he defied the basic belief of Aristotle. And we have shown that if it is a stone and if it is the mass of the earth, both the masses are getting cancelled out in finding out the acceleration, because acceleration is force by mass. Force comes to this, mass gets cancelled out. And that is what exactly we are trying to show and prove, what Galileo has proved many years later, that irrespective of the mass, it doesn't matter. Velocity will always increase at 9.8. And if you're right at the equator here, then you're going to weigh less, because gravitational acceleration will be less, because you're far from the center. Whereas on the pole, it will weigh more, and the gravitational acceleration will be more, imperceptibly more, because you're nearer to the center of the earth. Thank you for watching this video and have a nice day. Stay safe and stay happy.